안녕하세요. My name is Tufi Saliba. I'm the author of TODA IP. My co-author Dan and I would be happy to assist each and every one of you if you guys are interested further beyond this. This is just a 50-minute condensed lecture, and would be happy to facilitate any collaboration afterwards. All the material that you will find, they are not intended, they're mainly intended for developers. We are developers, but we're trying to change that and make it a little bit more suitable for academics, and try to get a lot of academia to help participate in this initiative. All right, so let me go through some slides here. So the TODA IP, it's security first internet communication protocol. Why do we need it? We start with that, and then we can justify why it's so important to have something like this. So for the longest time on the internet, when we are exchanging anything of value, we depended on a third party. If the exchange of information is not, a thing of that it's, let's say, valuable or whatnot, then you wouldn't really need to worry about having the dependency on a third party. But when something is valuable, you really care, because it ends up increasing the friction if the third party are going to do their job correctly. So you end up with the conundrum where you either have to increase your cost, time, and money in order to get something secure, or you end up having to lose that thing of value. So what did we do to have that third party? For the longest time, we were dependent on things like ledgers for real estate, for cars, for money, and so on and so forth. Now, there's certain characteristics of something that is of value. If more than one person can have ownership of it at the same time, then it might lose its value, such as money. Money has, for example, if I were to send you an email, you'd make a copy of that email, you can share it with tons of people. But if it's money that I'm sending it to you, you need to make sure that it's unique. So for the longest time, folks are dependent on third party. The third parties, how do they take care of that? They ended up having to build ledgers, because there's so many people that they depend on that third party, that supposedly the both sides, they need to trust in order to communicate. So when you do trust that third party, you end up consuming a lot of time and money, and that is the intent, is to eliminate that friction. Anything in this universe, if you reduce the friction, end up getting faster movements. So 11 years ago, we've started seeing certain explorations with a ledger that is replicated across the globe. As you all know, it's called Bitcoin. It works phenomenally well until certain, I don't want to say attacks or whatnot, but it's mainly exploitation of that protocol that got the evolution of it, rather than to be progressive, to be a little bit regressive. And then now we yet depend again on that third party that it's called miners or whatnot. But of course, folks, they don't like to admit to it. Third parties, they don't necessarily like to admit that they are a dependency or they are friction and so on and so forth. Of course, it's against their business. However, the smart ones from the third parties, they do realize that the potential can be a lot bigger, and they start partnering with us very recently. You can't say all of them, but some of them. Now that we feel extremely confident to start giving it to the academic world and so on and so forth. I'm giving this lecture. We've been trying to keep things as hush-hush as possible, just so we were able to get to the point where we are about 18 months ahead of the curve before we start publishing stuff. Let's go through the deck and hopefully we can cover all the aspects. There's some slides that I'm going to go through very quickly. First, Antoine Laurent de Lavoisier was a physicist, French physicist, and he said, rien ne se crée, rien ne se perd, tout se transforme. Nothing gets created, nothing gets lost, everything gets transformed. This is extremely important to start with this because many people, if they were to search me or whatnot, and they would think that I'm a maximalist in one way or another. I'm actually I try to be as inclusive as possible. Of course, you will find this thing online. It says, one Satoshi per $1. I've presented this many times. I work on technical necessities to get us there and not necessarily doing speculations or whatnot. The current state of Bitcoin, and that's based on today's reality. If we were to continue with the growing, cost to mine one Bitcoin, and that's been steady for the last 10 years. But if we were to continue the same way, we would end up with about $100 billion of electricity every 10 minutes. When you know that the math doesn't work in a certain direction, folks start listening a little bit more, luckily, if they're able to do the math. So, however, at the same time, there's a lot of false information out there. People, they talk about the single transaction footprints of Bitcoin. When you do run a transaction Bitcoin, it's not the only thing that is happening. It's actually keeping the certain value that you have secure. So part of that cost is to keep it secure and not necessarily to just transact it. It's like you're keeping something in the vault as opposed to transacting it. But also the transaction is necessary for it to be of value. Otherwise, if you cannot transact it, then it's moot to have something of value that you cannot transact. So, but that does not mean that the only use of the system is to transact and having to put everything under that single transaction. Other things that are extremely important to look for and to justify the raison d'etre of why we need something like that, why we need security first, what kind of future we could be heading towards. When we look at the lot of dependencies on AI and how crypto, as in cryptography, can help us ensure a better future for next generations to come. The smartphone today look like this, as you all know. And as we evolve more and more into the future, especially in pandemics like this, people did not believe what I said about a couple of years ago, that the future smartphones will look likely like this in 2030 plus. And that's a pill you swallow. It has all of the essential elements of a smartphone, along with some elements that perhaps exterior to your body and whatnot. Of course, this is more to say that it's going to be part of you somehow. Not necessarily to be a pill. There are a lot of initiatives working on something like this, and imagine when you have something of value that you depend on a third party that might betray you. Now you start realizing of how important it is to have security first, and when you feel that you need to trust that centralized AI or whatnot, they promise not to betray you, but we've seen otherwise. There's a general rule in the world: if they can, they will. So perhaps you can build the future where they cannot, as opposed to they will not, for generations to come. I apologize if I'm putting here Mark Zuckerberg. It's not intended to be against Facebook. We love Mark, and we really think it's very well intended. Truly, I mean, but some folks, they do things in a different way, and they may not necessarily be understood. So not only Facebook invading privacy, for example, in the name of security, a lot of folks, they do it everywhere on this planet. So that's privacy, but you know, frankly, if privacy is the only concern, people perhaps they don't really care much. But when it's like your entire asset and your entire willpower, your capability of deciding what you want to eat, when you want to wake up, and so on and so forth, there are a lot of scenarios we don't have to go through, but each and every one of you can imagine of how much we depend on online transactions, and imagine the dependency on third parties, how big it's becoming, and if it can betray you. If there are 500 people today that can get access to your smartphone, if that smartphone is a bill, would you give that bill to your children? However, if we have something that is called a decentralized bill or autonomous decentralized governance, perhaps everyone would want to take that bill as opposed to the centralized bill that can be controlled by third party. So now, before we get into the lecture, quick intro, who am I? Like I said, my name is Tufi Saliba. I'm involved in a lot of these organizations that you see on the screen, plus many more. Most recently, I took on the Global Chair for AI Standards for the ITFE. And that's extremely exciting because I've been working on some of these things that I've expressed earlier. But my business is TODA and things that revolve around TODA. And I was asked to provide a lecture on TODA IP, and this is what I'm doing here. So background, I've been in building startups pretty much all my life. Built 15 startups, failed 11 times, succeeded 3 times. Pretty good ratio. And I'm, if you do the math, there's a 4th one. Kind of became an Intel company at this present time, hasn't exited yet. We don't know if it will exit or not, you know, but I'm optimistic about a lot of the startups that I'm involved in, and a lot of the projects. Some of them, they're big companies, Fortune 500. Some of them, they're small startups. I'm inclusive. I work from the edge of Bitcoin to the edge of BPI and Financial Services Roundtable, but now it's called BPI, and from United Nations to any other NGO and nations. And all right, so enough about me. I can come back to this, but this can give a very good example on how TODA is being used today. And I will get into how it is being implemented with systems like Bitcoin, but I decided to start with deterministically combating deepfake because many people would think that a system like TODA can only be used as money. It is not the case. When we say security first, security is for anything that is valuable. All right, so you've all heard of deepfake. For those that haven't, deepfake is the ability to have AI being utilized behind the engine that it's filming you, but the output would look like, let's say, someone else saying a certain thing. Let's say it says like Donald Trump is launching nuclear weapon against North Korea or whatnot, and people, they see and hear Donald Trump, they might believe, and that can be, they can cause a lot of threat globally. Fake news, fake information, you name it. All of that can be expanded and how should I say that? I mean, a lot of folks, they utilize AI to build deepfake, to target certain folks with fake news and so on and so forth. And that's happening today. If we were to think about the future, is what I've given earlier with that bill, but this is happening today. Fake information, fake news. If you were to pick 10 presidents of nations in the world today, randomly, and you were to ask them to give you a brief of the news for the last 24 hours, certain topic, you're likely to get 10 different versions. So now I'm going to show how something like this is built on TODA in a hackathon 48 hours. Just so you all know, many people attempted to build AI to combat AI, and that's the wrong approach. If it works today, it's not guaranteed it's going to work tomorrow. We need something deterministic. So when folks came and approached me in this hackathon, and they said, how can we do something, I started brainstorming with them. So in this specific example, let's think of every minute of video, or every slide of video if you want, or every image. Basically, most videos have about 28 to 30 images per second. So if each and every one is hashed, cryptographic hash function will give you an output that looks like this here on the screen, as you can see where I'm pointing. And then some other video that it's being hashed around the same time will get into cryptographic hash function. Some other people might be running transactions, not necessarily videos, might be doing a lot of things, also can get hashed. Now, if I'm Donald Trump and I sign that video, every one of those slides, there's something that we're calling a temporal coupling. And how do we determine that temporal coupling is what I'm going to cover in a world that is being built on TODA. So if my device is generating that hash function, someone else's device generating the other hash function. Together, we can put them in, we can do some sort of temporal coupling, put them on one, and then other people, they can be doing the same thing. And the combination of all devices into the network can build something called the Merkel tree. So in order to explain this, we need to go through the Merkel tree a little bit. And for those that are not familiar with Merkel trees, it's just basically a binary tree, a specific type of binary tree where it's a hash of, every two hashes they're hashed, and then they're hashed again and hashed again. So, end up with one single hash on top of that Merkel tree. It's called the Merkel root. That kind of represents all of the hashes in that binary tree. Effectively, for those that are not familiar with the cryptographic hash function, that's basically giving you the ability to take any set of data and get an output like this one that I've showed you earlier. And this cannot be reversed. You cannot go the other way. It can only go one way. I'm going very quickly on those kind of things. You can research them elsewhere. There's a lot of things online. I'm going to assume that you guys know what the cryptographic hash function, what the binary tree, and in order to build that Merkel tree. However, most systems out there that build that Merkel tree, they build it in a single device. That's not the case in TODA IP. This is the cool thing about the TODA IP. So it does something that's called temporal coupling. So let's go here, and then for many of you, I'm going to assume that you do know how Bitcoin works. So with this one here, so let's say that there's an actual transaction and someone else is doing an image or whatnot. Now let's imagine in the case of Bitcoin that each and every Satoshi is the smallest unit in Bitcoin. Each and every Satoshi, let's say it is represented in a network packet or a file. Now, that file has a unique number universally, and that number is not being insured by a single entity. that number is being insured by something that it's called the TODA tree, which is a huge binary tree that is imaginary, basically a data structure. That imaginary binary tree, the definitions of it, they are spread out across every single device. They know how to construct that tree. However, when you have each and every Satoshi has a unique number universally, another thing that it's has that the protocol can ensure, and it belongs to a single signing device in every block of time. So in this block of time, this specific Satoshi, say it belongs to this device up here. Now this is simplified binary tree. Imagine this is 256 levels, simplified down to 5 levels. Of course, you can imagine 256 levels. Cool thing about binary trees is that although you can imagine them, you cannot build them even using all the computers in the universe, like a big tree with 256 levels. To put things in perspective, at level 160, you end up with points on that tree higher than the estimated atoms in the universe. So 256 is like a lot of numbers. So each and every number can only belong to a single device in every block of time. So that's some of the characteristics that it has. Now, how does it ensure that? If I were to be taking this number and moving it from here to someone else, what I would be doing is cryptographically signing that number to another owner. But that's not sufficient. We said in every block of time it belongs to a single owner universally. I need to do something to impact something that is global. While I actually send this Satoshi to someone else in this transaction, cryptographically I'm inserting inside that file the signature, my signature that I'm taking it from me to the other person. Inside that file, there's information sufficient to assure the other person that I own. In this specific block of time, I own that specific packet. How can I ensure that? So now let's follow through when I send it to that other person. I take it from my wallet, I sign it to the other person's wallet. In this specific block of time at this specific time, say it's like 3:20 p.m. On March 29th. If the other person needs to retransact it after 6 months from now, they can prove to anyone anywhere in the world that they own it as of this moment, because everyone, they have one thing that is replicated on their devices, which is that Merkel root. The creation of the Merkel root is done by a lot of devices across the network. Every single device could participate in it. Every single device is a node in TODA. Effectively, a pseudo-random function can select which devices they can take which packets or files through the creation of that Merkel tree using distributed computing. Deterministic distributed computing. That is the key. So effectively, we end up taking each and every number that has a unique number. By looking at that number and looking at the last 2 block hashes, we're able to generate a list of about 32 devices that they can manage it in this block of time. Next block of time, different 32 devices they can. That pseudo-random function is extremely important. Each and every aspect, every single word that I'm saying is extremely important. You take the ownership and assign it to the other person inside that file and give it to any one of those 32. Why you want to do this? Because you want the other person to accept that transaction. You have an incentive of why you're sending it to the other person. Now, the other person has the incentive to see it impacting the global hash of the block that is happening right now. So 6 months from now, they can take that and give it to anybody anywhere in the world and show that anywhere in the world, that any device, they have the hash of the block that happened today. What contributed to the creation of that block is this specific transaction, this insertion into that file, along with a lot of videos that they were happening at the same time, which they work similarly into being inserted into different branch of that tree, but getting to the same Merkel root. Effectively, everything that happens in this world can be time-stamped, and due to the deterministic distributed computing, we're able to run it without having to depend on a third party. This is a breakthrough. It has not been done before. Every single attempt that tried to do something like this, you have to depend on some third party, call themselves miners, yada, yada. Now, of course, a lot of you might be thinking about many different attack vectors, especially the cryptographers. You might be thinking, what if I build 1 million devices in my basement? They're fake devices. They're actually, virtual devices, and pretend to be part of the network. Of course, you can do this, but one of the cool things about TODA is that it can ensure that that pseudo-random function, as it's selecting devices from across the globe, it's selecting them using the previous 2 block hashes and the number of that file. So if you're running those 1 million devices in your basement and you happen to have some location somewhere on this planet, you have to have some location somewhere on the planet. One of the characteristics of having a system that is global, that is dispersed globally, is that the other nodes, they're dispersed anywhere across the globe. So it doesn't matter how much computing power you have in your basement, the likelihood for a random person crossing the street close to me to do temporal coupling back and forth and hit me about 53 times my device in 1 minute is a lot higher than your basement that could be in a different continent or different city, or even, in the same city but a little bit further away. Why? Because the laws of physics tell us that there's nothing that travels faster than the speed of light, and the network attempts to get to the speed of light. We barely get to the 2/3 of the speed of light. If you were to have an attack that to win ahead of any dispersed device anywhere in the world, and you're running those devices in your basement, you need to have a network that is a lot faster than the speed of light. This is an extremely important characteristic. We must depend on certain elements that they cannot be broken by, next evolution of computing and so on and so forth. The speed of light is constant in this universe. Now, of course, there are some attack vectors. People can say, it's like, what if they disperse those devices in a lot of places across the globe? And what if they compromise every single device and all of those? Every single one of those attacks, they're basically more costly than what you could get from the attack. Every single one of those attacks, they can be applicable to any system anywhere in the world. We have to realize that there's certain assumptions that they cannot be changed, and they are applicable to every single system anywhere in the world. So the file, the packet structure, it's usually, it's like, you know, the payloads, 2 to the power 12 bytes maximum. It's the creation cycles, like the actual current global Merkel root. I'm happy to share the latest paper, which has all of the specifics, but here what I'm trying to do is trying to explain it so folks that they can have access to this video and get to play it again and again. If we were to go back now to the previous example, and let's look at the videos. If I'm uploading a video onto the network, my branch of the tree resemble the Bitcoin branch of the tree. The Merkle root is still the same Merkle root globally. Every single branch of that tree end up like going in one direction. Every 1 minute, we have a single hash of the entire block. How many transactions, how many users can be part of that 1 minute? It's in the trillions and trillions. I mean, if you were to do any binary tree, and you were to go through every 10 levels of how many levels you can go, like in Bitcoin, you maximum need about 53 levels. And in 53 levels, you basically, why is it 153 levels? Because that's all the, actually all the Satoshis that can ever be created, they get to the 51 levels, which is 2 to the power 51. So if there are trillions of videos that are being created per minute, and there are billions of devices, every single device responsible for their videos, they can put them as part of this, and you still in a single hash, you're able to get all of those videos. This is extremely important because we do talk about efficient scalability, and before I get to the efficient scalability, we talk about security by design first. So effectively, we need to get to 5 elements, and all 5 combines that can give us the ability to that global, I would say, global penetration, whatnot, for the next internet, if you wish, or the next evolution of the internet. Security is number 1, and efficiency, as it is relevant, you know, it's always relative to whatever system when you say efficiency. But revolutionary technology, they had the thing in common that they usually have more than 90% more efficiency than the previous system. So we must have certain metrics and be able to measure that this new system can be built, if it's built on TODA or whatnot. It can have over 90% more efficiency than the previous centralized system and decentralized. Current decentralized systems, they don't have the efficiency by design by any means. They certainly have higher security than centralized systems, but they lack that other element, which is efficiency. Of course, you all know that they don't even have the confidentiality by design. They're ledgers that they've shared with everyone. In this specific one, let's talk about the confidentiality. So we did cover of that devices, they're part of the network. They're the ones that run the network. We know about this resilience and the security due to the formula that I've just described of how we're able to build the system using DDC, which is part of the proof of work in TODA. Uses the work part. The work part is deterministic distributed computing. Okay, so it is still proof of work, but we don't use Hashcash. Thank you, Hashcash. Over 20 years, it's been used phenomenally well. That's great. But Hashcash is just guessing numbers. This one, it's utilizing the computation that is needed to run the system itself and proving on that. So you end up with deterministic distributed computing instead of the hash cache. So a lot of work, but the proof is instantaneous. So the efficiency and then the confidentiality is that if I'm sending you a transaction, if you're sending someone else a transaction, who knows about this transaction? Well, every transaction can be, 20 or 30 of those files, maybe 100. Each and every one of those files, they get to be shared with up to 32 devices. What is shared with those devices? They're basically the hash of that. They cannot reverse that. They can take it and put it on this. Nobody really knows about this specific transaction but you and me. Whoa, now a lot of people might be thinking, well, we wanted confidentiality, but not this much secrecy. Well, the reality of things is that when you have this much confidentiality and certain laws in certain nations says that you cannot have this much, you must share some of those information with certain government or whatnot, you can certainly share that. But by design, it is confidential. When something is by design confidential, you can go from that point to make it a little more broad or whatnot. The fourth element is the scalability. We don't want the scalability without having the first three. You don't want scalability if you don't have security. You don't want scalability if you don't have efficiency. You do not want scalability if you don't have confidentiality. Those are three essential elements to then talk about scalability. How does a system like that, if you're building a system on TODA to do those videos that I've explained, or any other system, a lot of folks would talk about the scalability, millions of transactions per second. If you were to be building a system on TODA, we couldn't really get, when we had 800 devices spread out globally, we couldn't really get to more than 1 transaction per second. Shocking. Many people, they thought, okay, scalability, we're going to talk about millions and thousands and quadrillions of transactions per second, like every single claim that is out there, but they're running databases or centralized entity or that third party. On TODA, you only get 1 per 800 devices. Like I said, this lecture is intended to ITFE, and all the audience, they know how to do the math. When you have 800 devices, what happens when you have 800,000 devices? Using the same method that I've described, you get to 1,000 transactions per second, provably. 800 million devices, you get to 1 million transactions per second, and so on and so forth. So effectively, we're able to now build a system that can incorporate videos, health records, monetary transactions, you name it. And we don't depend on the third party. We don't depend on database. We don't depend on cloud. None of the above. And, that doesn't mean you cannot have those third parties provide service. The service layer will always exist to be centralized. Service layer can be, let's say, a database, can be however you want it. It's still centralized. They're coming to you for business. They're not going to really, care, or maybe some they would care depending on what you're dealing with. But when somebody's coming to you for business, you're still a centralized entity. You are a centralized entity. You provide them with that service. They're coming to you. Service layer can be centralized. It's a dependency layer here that's removing it to be decentralized. Autonomous decentralized governance is what we're talking about here. When we talk about decentralized, a lot of folks that come and show me certain methods of decentralized, hand wavy or 100 nodes that they are owned by 100 people, whatnot. Like, we're not really talking about democracy here and how you're gonna govern, certain systems. Frankly, if you were to look at existing organizations, corporations, they have phenomenal governance model, way better than a lot of those newbies that they're coming in and saying, it's like, oh, we figured out like how to do governance on Ethereum or on EOS or whatnot. I mean, come on, like, that's not gonna be revolutionary in any shape or form with its current design. So the evidence, I mean, if you were to look at the actual current blockchain penetrations, they're less than 0.2%. Something that is revolutionary, you wouldn't be stuck at that. But we're optimistic we can get to the remaining 99.8%, even if at the time we're going to call it an anti-blockchain. We don't really care about the name blockchain much. So I think I've went through the most important elements of TODA. As I'm going through a little bit more, I'm going to stop the recording here, and then I will resume for the remaining 10 minutes to make sure that we cover everything. So it might look like I'm stopping and then restarting, and just simply to make sure for the last 10 minutes I'm covering most important. All right, so now that we have covered essential elements of how TODA protocol works, certain implementations, how to build on TODA IP. We can talk about some of the opportunities. For example, if you were to look at Bitcoin on TODA, for example, instead of today, the dependency layer is the, the things that they're in the middle, they call themselves miners. Now let's imagine that is split between service layer and the actual dependency layer are the devices across the globe. Perhaps that can get us to the remaining 99%. There are a lot of other opportunities like I discussed earlier with the anti-fake information, anti-deepfake. There are a lot of use cases that a lot of phenomenal people they try to bring onto blockchain, whether it is running AI or running decentralized AI marketplaces to health records, to anything of value basically at the end of the day. But I mean, if we were to have a system enable a future where somebody is going to say, I'm going to compete with the centralized system that exists today, and they're able to have more than 99% reduction in friction or more than 99% efficiencies, then we are likely to have something that is revolutionary. Some examples from nature, certain things they run, the alveolus capillary protocol. It's basically, as you're watching this, as you're hearing my words each and every second, in your lungs, billions and billions of carbon dioxide is exchanged with oxygen in a fully decentralized setting. And this doesn't really check with your brain and ask for permission and so on and so forth. And you can use this as a method to think of like, okay, do we have to really check with the central entity every time we're doing a certain thing? Maybe not. It can do it fully compliant by design. And that's the intent here. If you worked hard, let's say for your money, you own your money, you can exchange it with someone else, you can send it to someone else without having to ask permission for a third party. Similarly, whether it is your health record or other things that you are, you see it as of value. So other opportunities that, global standards, we care a lot about global standards because they basically build standards in a way that everyone can look at those standards and they're able to put on their devices certain standards in order to communicate effectively. We hope that we can compel a lot of people, a lot of academics to start working on the TODA IP. It doesn't have any coin or token or anything like that. I mean, it is technology. It's to boost the utilizations of technology in general by reducing the friction tremendously because it has security by design. And to have a better future for the generations to come, by having that security by design, like that example that I gave on the pill, we're able to provide a future that that we can depend on, that not dependent on centralized entities. They promise us not to break certain rules. In the current pandemic, there are a lot of folks talking about how each and every human in the future will have to have a certain bracelet or whatnot, or whether it is a pill or some other elements that they can ensure that they don't have a certain virus, so then others they can communicate with them. That can also be built in a fully decentralized setting where you're in full ownership of your own data. And there's a lot of methods using zero knowledge proof of how that can be done without having to depend on third parties. As much as a lot of folks, they think that depends on third party is a good thing, but when you give them certain examples of who is the third party, who could be managing it, and so on and so forth, it's frightening. Which can lead us to certain things to think of, like, for example, if you were to think of most efficient and successful way of killing cancer, the same way like many of the solutions that are being built today, it's just, invade privacy in the name of security, or let's just do a lot of things in order to achieve results very efficiently. We just end up like, having control over the people or whatnot. Maybe there's a better way, and we know there's a better way. We used to say we believe, now we know there's a better way. We hope that a lot of the world, know that as well, because the most efficient and successful way of killing cancer today, as you all know, is killing the host. I'm hoping we don't go in a direction where we have to kill the host in order to kill cancer. For a lot of you would like to get in touch, please reach out. There's my LinkedIn, there's like my email, phone, and so on and so forth, or the organizers of this event. I'm hoping that the situation would be better in the world soon, and then we'll be able to meet in person. 감사합니다. 안녕히 계세요.